There's one section of the Security Plus exam that fails more candidates than any other. It's not networking, it's not threats, it's cryptography, and inside cryptography, public key infrastructure. Most courses cover PKI in a single slide with a lot of arrows. They tell you a CA signs a certificate, the certificate has a public key, and somewhere there's a chain of trust. Then you walk into the test and the question asks you the difference between a CSR, a CRL, and OCSP stapling, and you realize you never actually saw a certificate. We're going to fix that today. In the next 60 minutes, I'm going to take you from the basic math of encryption all the way to running your own certificate authority, issuing certificates, and breaking down a real TLS handshake step by step. We will cover symmetric and asymmetric encryption, hashing, digital signatures, the entire X509 certificate format, and every PKI concept on the SY0701 objectives. And we are not just going to talk about it, we are going to build it. Real terminals, real openssl commands on both Linux and macOS. You'll watch a private key get generated, you'll watch a certificate get signed, and you'll watch a browser verify the chain, exactly the way it works in production. This video is structured into 14 chapters with chapter markers in the description so you can jump around. If you're studying for Security Plus, watch it end to end at least once. If you're a working engineer brushing up on PKI, the chapter list is your friend. Grab a coffee. Let's get to it. Get to. Every single time you see a padlock icon in your browser, every time you SSH into a server, every time your iPhone verifies an iOS update, every time a Tesla pushes new firmware to itself overnight, all of that is cryptography. It is the single most important defensive technology in computer security, and the Security Plus exam expects you to understand why. Cryptography delivers 3 of the 4 pillars of information security: confidentiality, integrity, and authenticity. Confidentiality means only the intended recipient can read the message. That's encryption. Integrity means the message has not been changed in transit. That's hashing and digital signatures. Authenticity means you can prove who the message came from. That's also digital signatures plus certificates. Notice that availability, the third leg of the classic CIA triad, is mostly outside crypto's job. Crypto cannot help you if the server is offline, but everything else, crypto. The exam will ask you to map crypto controls to threats. 3 threats matter most. Number 1, eavesdropping. Someone on the same network watching your traffic. The defense is encryption, symmetric for bulk data, asymmetric for the key exchange. Number 2, tampering. An attacker modifies the data while it's in flight or while it's stored. The defense is integrity, hashes, message authentication codes, signatures. Number 3, impersonation. An attacker pretends to be a trusted party. The defense is authentication, certificates issued by a CA you trust. Every PKI question on the test is, at its core, a question about which of these 3 threats is being addressed. With that frame in your head, let's get into the actual mechanics. We're starting with symmetric encryption, one shared secret key, used for both encryption and decryption. It's the workhorse of crypto, it's where AES, the Advanced Encryption Standard, lives, and it's where Security Plus expects you to know your modes, your key sizes, and your trade-offs. Chapter 2 starts now. Symmetric encryption is the simplest idea in cryptography, and it's also the workhorse that protects almost all of your data, at rest and in transit. The setup: one shared secret key. Alice uses it to encrypt a message. Bob uses the exact same key to decrypt it. Same key, both directions, fast, efficient, and, until the late 1970s, every important cipher you've heard of: DES, triple DES, AES, ChaCha20, all symmetric. The dominant symmetric cipher today is AES, the Advanced Encryption Standard, standardized by NIST in 2001 after a multi-year public competition. AES operates on 128-bit blocks and supports 3 key sizes: 128, 192, and 256 bits. For Security Plus, you should know all 3 are considered secure today. The difference is computational cost versus paranoia. 128-bit AES would take a current supercomputer roughly 10 to the 21st years to brute force. AES 256 is the FIPS validated choice for US government top secret data. If you remember 3 things about AES on the exam, it's a block cipher, the block size is 128 bits, and the key sizes are 128, 192, or 256. Now here's where the exam loves to trip people up. Modes of operation. A mode is how a block cipher handles data longer than one block. There are 3 modes you must know. ECB, Electronic Code Book, encrypts each block independently. Identical plaintext blocks produce identical ciphertext blocks. Visible patterns survive encryption. ECB is broken. Never use it. The exam will give you ECB as a wrong answer. CBC, cipher block chaining. Each block is XORed with the previous ciphertext block before encryption. Identical plaintext blocks no longer look alike. CBC requires an initialization vector, an IV, and the IV must be unique per message. CBC is still seen in legacy systems but doesn't provide authentication. GCM, Galois counter mode, turns AES into authenticated encryption. You get confidentiality plus integrity in one operation. GCM produces a ciphertext and an authentication tag. Any tampering with the ciphertext makes the tag invalid. This is the modern default. TLS 1.3 only allows authenticated modes. If you see AES 256 GCM on the exam, that's the right answer. Let's see it work. We create a file encrypted with AES 256 in GCM mode, look at the ciphertext, and decrypt it back. Notice 3 things. 1. We use the flag dash PBKDF2, that's PBKDF2, a key derivation function that turns our password into a proper AES key. 2. The encrypted file looks like random noise, no pattern. 3. Decrypting with the same password recovers the original perfectly. If you change 1 byte of the password or 1 byte of the ciphertext, GCM refuses to decrypt and returns an error. That is authenticated encryption doing its job. Symmetric encryption is fast and battle-tested, but it has one giant unsolved problem. How do you share the secret key in the first place? You can't send it over the internet. Anyone listening would steal it. You can't hard-code it. Every user needs the same key. This is the key distribution problem, and it's the entire reason asymmetric encryption was invented. Chapter 3. Asymmetric encryption, sometimes called public key cryptography, was invented in the late 1970s to solve the key distribution problem we just left hanging in Chapter 2. The trick is mathematical sleight of hand. Instead of one shared secret, every party has a pair of keys. One key is public. You can shout it from a rooftop, post it on your website, hand it to strangers. The other key is private. You protect it like your toothbrush, and it never leaves your machine. Anything encrypted with the public key can only be decrypted with the matching private key. That asymmetry is the magic. Here's how it solves the problem from last chapter. Bob publishes his public key. It's literally on his web server. Anyone can grab it. Alice wants to send Bob a secret. She encrypts her message using Bob's public key. Only Bob's matching private key can decrypt it. Eavesdroppers can capture the ciphertext. They can capture the public key. They cannot decrypt the message because they don't have Bob's private key. Notice, Alice and Bob never shared a secret in advance. They never met. The math itself enforces the privacy. That is genuinely one of the most important ideas in computer security. The first practical public key system was RSA, named after Rivest, Shamir, and Adelman, the 3 MIT cryptographers who published it in 1977. RSA's security rests on the difficulty of factoring very large numbers. You multiply 2 large primes together to get your public key. To break RSA, an attacker would have to factor that product back into the original primes, a task that takes longer than the lifetime of the universe for keys of reasonable size. For Security Plus, you need to know 3 RSA key sizes. 2048 bits is the practical minimum today. 3072 is recommended for new deployments, and 4096 is what you reach for when you want extra margin. Anything below 2048 is considered weak. RSA is old and big. Modern systems prefer ECC, elliptic curve cryptography. ECC gives you the same security as RSA at a fraction of the key size. A 256-bit ECC key offers roughly the same security as a 3072-bit RSA key. Smaller keys mean faster operations, less bandwidth, lower battery cost, which is why TLS 1.3, Signal, Apple's Secure Enclave, and basically every modern protocol use ECC by default. Then there is Diffie-Hellman key exchange, the third algorithm Security Plus expects you to know. DH lets two parties who have never met derive a shared symmetric key over a public channel without ever transmitting that key. Modern systems use ECDH, the elliptic curve flavor, for TLS 1.3, SSH, and Signal. The property to remember: DH is for key exchange only. RSA and ECC can do both encryption and signatures. Let's see it work. We generate an RSA 2048 key pair. Private goes in private.pem. Public gets derived from it. Notice the public key is a small text file you can email, paste in a chat, host on a website. It does not compromise the private key. We write a message, encrypt it with the public key using openssl PKI and decrypt it with the matching private key. Only the holder of the private key can read the message. One practical note: this kind of direct public key encryption is rarely used for bulk data. It is slow, and there are size limits. In practice, you will see asymmetric used to exchange a symmetric session key, and then symmetric handles the bulk traffic. That hybrid pattern is exactly what TLS does, and it is the answer to, if asymmetric is so great, why do we still need symmetric? You need both. We now have two of the three things we need for real-world security: a way to share keys without meeting in person, and a way to encrypt bulk data quickly. The missing piece is integrity. How do you prove the message you received is exactly the message that was sent, not changed by a single bit on the way? For that, we need hashing. Chapter 4. A hash function is a one-way fingerprint of data. You feed in any amount of input, a single letter, a 10 megabyte PDF, the entire works of Shakespeare, and out comes a fixed length string of bits. For SHA-256, that is always exactly 256 bits, written as 64 hex characters. The output is called a hash, a digest, or a fingerprint. Same input, same output. One bit different, completely different output. That is the magic. A hash is cryptographic only if it has four properties. One way. Given the hash, you cannot reverse it to find the original input. Even with infinite computing power, you would just be guessing. 2. Deterministic. The same input always produces the exact same output. 3. Avalanche effect. A one-bit change in the input produces a wildly different output. 4. Collision resistant. It is computationally infeasible to find two different inputs that produce the same hash. If any of these properties break, the hash function is considered broken. That is why we no longer use MD5 or SHA-1 for security. Real-world collisions have been demonstrated. The secure hash algorithm family. SHA-1 is broken. Google demonstrated a real-world collision in 2017. Do not use SHA-1 for security. SHA-2 is the current standard. The most common variants are SHA-256 and SHA-5112. The number is the output size in bits. SHA-256 is what Bitcoin uses, what Git uses, what TLS certificates use today. SHA-3 was standardized in 2015 as a structural alternative. It exists in case SHA-2 ever has its day of reckoning, but for now, SHA-2 is fine. For Security Plus, SHA-1 is the wrong answer. SHA-256 or above is the right answer. Two practical uses you must know. HMAC, hash-based message authentication code, combines a hash with a secret key. The result proves not just that data was not changed, but that it came from someone who knows the key. HMAC sits at the heart of TLS, JWT, and API request signing. The second use, salting passwords. You never store a raw password, and you never store just its hash, because attackers pre-compute hashes for common passwords. Instead, you add a unique random salt to each password before hashing and store both the salt and the hash. Same password, different salt, different stored hash. bcrypt, scrypt, and argon2 are the password hashing functions you should reach for. Let's see it. We hash a file with SHA-256. We change one character, adding an exclamation point, and hash again. Look at the two outputs. They differ by a single byte of input, and the resulting hashes share zero recognizable pattern. That is avalanche, visible. Then we add an HMAC key. The output is different again because the hash now incorporates the secret. Without the key, an attacker cannot reproduce this output, even if they have the message. That is how HMAC gives you integrity and authenticity in one step. A hash proves the data was not changed. HMAC proves the data came from someone with the shared key. But neither of those proves the data came from a specific person whose identity you can verify. For that, we combine hashing with the asymmetric keys from Chapter 3. We sign the hash with our private key. Anyone with our public key can verify it. That is a digital signature. Chapter 5. We have encryption for privacy. We have hashing for integrity. The remaining gap is identity. When a message arrives, how do you prove that it actually came from the person it claims to come from? Encryption alone cannot prove this. Anyone could encrypt a message with Bob's public key, including someone pretending to be Alice. Hashing alone cannot prove this either. Anyone can compute a hash. The answer is digital signatures. Here is the flow, and it is worth understanding deeply. Alice wants to send a signed message to Bob. Step 1. Alice writes her message. Step 2. She computes a SHA-256 hash of that message. Step 3. And this is the magic. She encrypts the hash with her private key. That encrypted hash is the digital signature. Step 4. She sends both the original message and the signature to Bob. Bob's side. Step 5. He computes his own SHA-256 hash of the message he received. Step 6. He decrypts Alice's signature using Alice's public key. Step 7. He compares the two hashes. If they match, three things are simultaneously proven. The message came from someone who has Alice's private key. That is authenticity. The message was not changed in transit. That is integrity. And Alice cannot later deny sending it. That is non-repudiation. A reasonable question, why not just encrypt the entire message with the private key instead of just the hash? Two reasons. First, asymmetric encryption is slow. Signing a hash is hundreds of times faster than signing the full data. Second, asymmetric algorithms have size limits. RSA 2048 can only encrypt about 256 bytes at a time. Hashes are always fixed size. 32 bytes for SHA-256, 64 bytes for SHA-512, so the same signature scheme works regardless of how big the original message is. Where you see digital signatures, code signing, Apple, Microsoft, and Google all require that apps and OS updates be signed by trusted keys before they run. TLS certificates, every HTTPS site you visit, the certificate is signed by a certificate authority. JWT, the access tokens for most modern web APIs are signed with HMAC or with asymmetric keys. Email, SMIME, and PGP both use signatures to prove the sender. And the entire chain of trust in PKI, which is exactly where we are headed next, is built on digital signatures. Let's sign and verify. Using the RSA key pair from Chapter 3, we sign msg.txt with our private key. The signature file is exactly 256 bytes for RSA 2048. Now we verify with the public key. Verified OK. Then we tamper with the message. We append a single word. Same signature, we verify again. Verification failure. The signature only validates against the exact bytes that were originally signed. Change one byte, the signature no longer matches. Digital signatures prove identity if you trust the public key. But how do you know whose public key to trust? If I send you a public key claiming to be Alice, you have no way to verify that's actually her. We need a trusted third party who vouches for the link between a public key and an identity, that is a certificate authority. That is Chapter 6. Public Key Infrastructure, PKI, is the system that answers the question we left hanging at the end of Chapter 5. How do you know whose public key to trust? The answer is, you trust a certificate authority that vouches for it. PKI is the entire ecosystem that makes that trust possible. The players, the rules, the formats, and the protocols. For Security Plus, you need to know 4 players and 3 revocation mechanisms. We will cover all of them in this chapter. At the top of every PKI is a root certificate authority. The root's certificate is self-signed. There is no one above it. Root CAs are extreme guard-the-key operations, hardware security modules, off-network, multi-person ceremonies just to power up the key. If a root CA key is compromised, the entire chain below it has to be rebuilt. So root CAs almost never sign individual certificates directly. Instead, they sign intermediate CAs. The intermediates do the actual day-to-day work, issuing certs to web servers, code signing keys, employee email. If an intermediate is compromised, you revoke it and rotate without burning the root. This 3-tier structure, root, intermediate, leaf, is the standard model used by every public CA on the internet today. Here's how a certificate actually gets issued, and you should know this flow code for the exam. Step 1. The subscriber, that is you, your web server, your IoT device, generates an asymmetric key pair. Step 2. The subscriber creates a certificate signing request, or CSR, which contains the public key plus identity information like the domain name or company. Step 3. The registration authority verifies that identity. For a domain certificate, the RA confirms you control the domain. For a business validation cert, they check incorporation records. Step 4. Once verified, the certificate authority signs the CSR with its private key, producing the certificate. Step 5. The cert is delivered back to the subscriber. Critical detail: the subscriber never reveals their private key to the CA, only the public key inside the CSR. When your browser connects to a website, it does the trust check in reverse. The server sends its leaf certificate plus any intermediate certificates needed to chain back to a root. The browser walks up the chain. It verifies the leaf was signed by the intermediate, then verifies the intermediate was signed by another intermediate or by a root. The walk continues until it reaches a root certificate that the browser already trusts, meaning a root that ships pre-installed in your operating system or browser trust store. If the walk reaches a trusted root, the chain is valid. If it reaches an unknown root, you get the big red "not secure" warning. That is exactly why a self-signed certificate fails. Nothing in the browser trust store vouches for it. Sometimes a certificate needs to be invalidated before its expiration date. The private key was compromised, an employee left, an audit failed. PKI has 3 mechanisms for revocation, and the exam loves to ask you to compare them. CRL, Certificate Revocation List, is a signed list of revoked certificate serial numbers, published by the CA. Browsers download it periodically. Simple, offline checkable. But the list gets large and the updates are infrequent. OCSP, Online Certificate Status Protocol, is a per-certificate live query to the CA. The browser asks, is serial number such and such still valid? Real time. But it adds latency on every connection, and there is a privacy concern. The CA learns who you are visiting. OCSP stapling. The server prefetches the OCSP response from the CA and staples it into the TLS Handshake. The browser gets the freshness check without contacting the CA. No latency hit, no privacy leak. This is the modern default. So we now know what PKI is, who the players are, how a cert gets issued, how a chain gets verified, and how revocation works. But what does a certificate actually look like inside? What fields are in it? What do they mean? and which ones the exam will ask about. That is Chapter 7, the anatomy of an X509 certificate. Every certificate you have ever seen, TLS, code signing, S-MIME, client authentication, uses the X.509 format. It is an ITU-T standard, currently at version 3, that defines exactly what fields a certificate must contain. Once you can read an X.509 certificate, you can debug almost any PKI problem. So let's read one. Every X.509 cert has the same skeleton, version, almost always v3 today, serial number, a unique identifier the CA assigns. If the cert is ever revoked, this serial is what goes on the revocation list. Signature algorithm, what hash plus signing scheme the CA used. Today you should see SHA-256 with RSA or SHA-256 with ECDSA. Issuer, who signed this cert, expressed as a distinguished name with components like CN for common name, O for organization, and C for country. Validity period, not before and not after timestamps. Certs are only trusted in that window. Subject, who this cert is for, also as a distinguished name. For a web server, the subject's common name is typically the primary domain. After the basics come the parts that actually matter for security. Subject public key info is the public key being certified, algorithm, key size, and the bytes themselves. Then the extensions, which is where most of the real metadata lives. Subject alternative name, SAN, is the list of additional names this cert is valid for. Modern browsers ignore the common name field entirely and rely on SAN. If you have ever wondered how one cert covers example.com and www.example.com and api.example.com, it is all listed in SAN. Key usage and extended key usage describe what this cert is allowed to do. A TLS server cert has digital signature key encipherment plus TLS web server authentication. A code signing cert has different values. If a cert is presented for the wrong purpose, validation fails. Basic constraints is the most important security extension. If it says CA true, this cert is allowed to sign other certs. It is a CA. If CA false, it is a leaf. Misconfigured basic constraints is how some historical PKI attacks worked. Finally, the signature itself, the CA's signature over every field above, computed with the CA's private key. Two encodings you will see in the wild. PEM, Privacy Enhanced Mail, is the text format with the begin and end markers. PEM is human readable, easy to paste, and what command line tools and config files typically use. DER, Distinguished Encoding Rules, is the binary format, same data, just raw bytes. PEM is literally DER encoded as base 64 with a header and footer. They are trivially convertible with openssl. Let's read a real certificate. Running openssl x509-text on a Let's Encrypt cert produces this output. You can see the version, the serial number, the signing algorithm, issuer, Let's Encrypt R3, validity, not before May 1st, not after July 30th. Subject, example.com, subject public key info, RSA 2048 bits. Now the extensions. Subject alternative name lists, example.com, www.example.com, and the wildcard star.example.com. Key usage shows digital signature and key encipherment. Extended key usage shows TLS web server authentication and TLS web client authentication. Basic constraint says CA false, meaning this is a leaf certificate, not a CA, and at the bottom, the signature, the CA's RSA signature over everything above. If you can read this output, you can debug almost any TLS problem in production. You now know what is in a certificate. The natural next question is, how do you actually build one? In Chapter 8, we are going to build a complete certificate authority from scratch on the command line. Root CA, intermediate CA, server certificate. All signed properly, all chained, all verifiable. Chapter 8. This is the chapter Security Plus expects you to actually be able to do. We are going to build a complete certificate authority from scratch, root, intermediate, and a server certificate, all using openssl commands you can copy and run on any Linux or Mac OS machine. By the end, you will have a fully verified certificate chain, and you will understand exactly what every command did. Let's go. Step 1. The root. We start by generating a 496-bit RSA private key. That is the root secret. In production, this key would live in a hardware security module and never touch a network. Next, we use openssl rec to create a self-signed certificate from that key, valid for 10 years. The subject distinguished name identifies our CA. Notice when we inspect the result that the issuer and subject are identical. That is what self-signed means. The root vouches for itself, which is exactly why operating systems ship a hard-coded list of trusted roots. Anyone who trusts our root will, by extension, trust everything our root signs. Step 2. The intermediate. Same key generation as before, but this time we create a certificate signing request, not a self-signed cert. The CSR is what we hand to a certificate authority. In this case, the CA is our own root. We use openssl x509-rec to take the CSR, sign it with the root's private key, and produce the intermediate certificate. Two critical details. First, we attach a basic constraints extension that says CA true. That tells anyone validating this cert that it is allowed to sign other certificates. Second, the pathln. 0 caps the chain. This intermediate can sign leaves, but cannot create further intermediates below it. Now look at the issuer and subject in the final command. They are different. Issuer is the root, subject is the intermediate. That asymmetry is the signature of a properly chained certificate. Step 3. The server certificate. The leaf. RSA 2048 for the server key is plenty, since server certs rotate annually. The CSR subject is our domain. We use openssl x509-rec again, but this time we sign with the intermediate's private key, not the root. This is the production pattern. The intermediate does the day-to-day signing work. The root stays safely offline. We also attach a subject alternative name extension listing the domains this cert is valid for. Notice the result. The issuer is the intermediate. The subject is example.com. We now have 3 levels of certificate in the right relationship. The moment of truth. First, look at all the files we have created. Now we run openssl verify asking, does server.crt chain back to our root? Without the intermediate, we get error 20, unable to get local issuer certificate. That is the same error your browser shows when a server forgets to send its intermediate. The fix: include the intermediate as an untrusted parent during validation. Now openssl walks the chain. Server signed by intermediate, intermediate signed by root. Root is in our trust store. Result: OK. In production, you concatenate the server cert and intermediate into a single chain file, and your TLS configuration serves both. With the intermediate present, the chain validates cleanly. Stop and appreciate this. You now know how to build, sign, and verify every layer of a certificate hierarchy from scratch. That is a real engineering skill, and it is rare. Up next, we will zoom in on the CSR itself, what is in it, how to read one, and how the signing handshake works with a public CA like Let's Encrypt in the real world. Chapter 9. A certificate signing request, CSR, is the artifact you hand a certificate authority when you want a certificate. 3 things matter about it. 1. A CSR contains your public key, not your private key. Your private key never leaves your machine. 2. A CSR contains identity information, domain names, organization, country, that the CA will verify. 3. A CSR is itself signed by your private key, which proves to the CA that you possess the matching private key. That's the entire purpose of the CSR. Let's read a real CSR. Running openssl rec-text on server.csr produces this output. At the top, The subject, expressed as a distinguished name, common name example.com, organization, country. Then the public key info, RSA 2048 bits and the modulus. Then a section called requested extensions. This is where you tell the CA what kind of cert you want, subject alternative names, key usage requests, extended key usage. The CA can grant these or override them. It has final say. At the bottom is the signature, computed with your private key over everything above. The CA verifies that signature first. If it does not check out, the request is rejected immediately. On the CA side, 4 things happen. 1. The CA verifies the CSR's own signature, confirming you control the private key that matches the public key inside. 2. The CA or its registration authority verifies your identity. For domain certs, this means proving DNS or HTTP control of the domain. For business certs, it means showing incorporation paperwork. 3. The CA applies its issuance policy. It may strip your requested extensions, add its own, set validity windows, and choose a serial number. 4. The CA signs the assembled certificate with its private key. What comes out the other side is a fully formed X509 certificate, ready to chain back to a trusted root. In the real world, almost nobody types these openssl commands manually. The standard for automated issuance is ACME, the Automatic Certificate Management Environment, defined in RFC 8555. Let's Encrypt is the dominant public CA using ACME. Here is how it works. Your server runs an ACME client like certbot. The client generates a key pair and CSR. The client asks, "Let's encrypt for a certificate for example.com." Let's Encrypt replies with a challenge, typically, place this random token at /.wellknown/acme challenge /this file name. Your client publishes the token. Let's Encrypt fetches it over HTTP and confirms you control the domain. Then, Let's Encrypt signs your cert. Validity is 90 days by design, short enough that auto-renewal must work, which forces good operational hygiene. ACME is the reason TLS is now free and effortless for the entire internet. Let's run it. We create a CSR with the -ADX flag to embed a subject alternative name request right in the request. We use openssl rec-verify to check the CSR's self-signature, verify OK, then dump its contents. You can see the subject, the public key algorithm, and the requested extensions. Then we sign the CSR with our intermediate CA using the -copy _ extensions copy all flag, so the SAN we requested actually ends up in the issued certificate. Signature, OK. 90-day validity matching the Let's Encrypt default. Every cert we have built or read so far has validated one thing, that you control a domain. But the real world has many cert flavors, different validation levels, different shapes, different jobs. Domain validation, organization validation, extended validation, wildcards, code signing, client certificates. Chapter 10 walks through every type Security Plus expects you to know. Certificates come in flavors, and the exam expects you to recognize each. There are 3 axes to think about. Validation level, how hard did the CA work to confirm identity? Shape, what names does the cert cover? Job, what is the cert authorized to do? Let's walk all of them. 3 validation levels. Domain validation, DV, is the lightweight default. The CA only confirms you control the domain, usually with an automated HTTP or DNS challenge. Minutes to issue, free from Let's Encrypt. Around 95% of HTTPS sites use DV. Organization validation, OV, adds a check on the legal entity. The CA confirms an organization exists at a particular address, often by looking at government records or making a phone call. Hours to days to issue. The certificate's subject distinguished name will include the real organization name. Extended validation, EV, is the strictest tier, defined by the CA Browser Forum guidelines. The CA verifies legal status, physical address, operational existence, multiple identity proofs. days to issue, expensive, and required by some compliance regimes for banks and payment processors. Browsers used to show a green address bar for EV until around 2019. They have since removed the visual indicator, but the audit requirement remains. Two shapes: a SAN certificate, subject alternative name, explicitly lists every domain it covers. You can mix unrelated domains in one cert. Example.com, api.example.com, even cousins.org. This is the modern default for multi-domain hosting. A wildcard certificate uses a star at the leftmost position, star.example.com, and covers every direct subdomain. Two things to remember about wildcards. First, they only cover one level. Star.example.com matches www.example.com but does not match foo.bar.example.com. Second, the wildcard does not match the bare root. You have to explicitly add example.com as a SAN entry alongside the wildcard. The production pattern is a SAN cert that lists both the root and the wildcard. Two job-specific cert types: code signing certs, sign software, Apple Developer ID, Microsoft Authentic Code, the system that lets macOS Gatekeeper and Windows Smart Screen recognize this app comes from a known developer. Look at the extended key usage field. It has code signing. If a cert without code signing EKU tries to validate a binary, the OS refuses. Client authentication certs do the opposite of server certs. Instead of the server proving identity to the client proves identity to the server. This is mutual TLS, used in enterprise VPNs, CIAC and PIV smart cards in government, and SMIME email. The extended key usage field has client auth instead of server auth. Self-signed certificates have one place: development. A self-signed cert has no chain back to a trusted root, so every browser, OS, and TLS client will refuse it unless you manually trust it. Where they make sense: local development against HTTPS, internal lab gear, prototyping. Where they do not make sense: anything user-facing in production. Security Plus loves to throw self-signed as a wrong answer to a "which cert type would you use for a public web server" question. The right answer is always DV at minimum, and DV is free. You now know every certificate flavor the exam tests: domain, organization, extended validation, SAN and wildcard, code signing and client, self-signed. The remaining question: how does a certificate actually get used during a connection? What happens between your browser typing HTTP and the encrypted page arriving? That is the TLS Handshake. Chapter 11. You type https://example.com and press enter. Before a single byte of the actual page arrives, your browser and the server perform an entire negotiation, agreeing on encryption algorithms, proving the server's identity, and deriving a shared session key. That negotiation is the TLS Handshake, and Security Plus expects you to know its shape. Let's walk through it. The classic TLS 1.2 handshake takes 2 full round trips. Step 1. The client sends a client hello, listing the cipher suites it supports, plus a random nonce. Step 2. The server picks one cipher suite and replies with a server hello, including its own random. Step 3. The server sends its certificate plus any intermediates needed to chain back to a root. Step 4. The server sends a key exchange message. For modern systems, this is an ephemeral Diffie-Hellman public share signed with the server's private key. Step 5. Server hello done signals the server is finished talking for now. Step 6. The client responds with its half of the key exchange. Both sides now derive the same shared session key. Step 7. Client sends change cipher spec and an encrypted finished message. Step 8. Server does the same. From this point, all application data is encrypted with the session key. 2 round trips before any real data. That's the cost of TLS 1.2. TLS 1.3, standardized in 2018, fixes the latency. The client's first message, client hello, already includes its key exchange share. The server's first reply, server hello, bundles the certificate, its signature, and a finished message in one trip. That collapses the handshake to one round trip before encrypted data flows. With session resumption, a returning client can even send encrypted data in its very first packet. Zero round trip, or zero RTT. TLS 1.3 also removes every weak cipher from earlier versions. No more RC4, no more CBC mode, no more RSA key exchange. The only allowed key exchanges are ephemeral Diffie-Hellman variants, which give you forward secrecy by default. For Security Plus, TLS 1.3 is the right answer for any modern deployment. Let's actually inspect a TLS connection. The openssl s_client command opens a TLS session to a server and dumps everything that happened. You can see the certificate chain, server certificate at the top, intermediate beneath, and the root identifier. You can see the negotiated protocol, TLS 1.3, and the negotiated cipher, TLS_AES 256, GCM SHA-384, AES 256 for the bulk cipher, GCM for authenticated encryption, SHA-384 for the handshake hash. This is exactly what we covered in earlier chapters, now visible on the wire. The handshake works. The certificate is valid. Encryption flows, but certificates do not live forever. They expire, they get revoked, sometimes they leak. What happens across a cert's full life cycle, from issuance to renewal to revocation? Chapter 12. Every certificate goes through the same life cycle. It gets issued, it gets installed and used, it approaches its expiry date. At some point, it either gets renewed, looping back into use, or it gets revoked before its time. Security Plus expects you to know each stage and the operational practices that go with them. Let's walk it. Issuance. The CA signs your cert, you install it on your server, traffic flows. For Let's Encrypt style certs, validity is 90 days. For commercial DV/OV/EV, often 1 year. Renewal is the most common operational task. Best practice is to renew automatically at around 2/3 of the validity period. For a 90-day cert, that's day 60. Why early? It gives you a 30-day buffer to fix anything that breaks before users see an expired cert warning. Modern tooling, CertBot, Acme.sh, Cloud Managed Certs, does this on a cron. The Security Plus answer to how should certs be renewed is always automated well before expiry with monitoring. Revocation kills a certificate before its natural expiry. You already know the 3 mechanisms from Chapter 6, CRL, OCSP, OCSP stapling, but the exam will also ask when you revoke. 3 triggers matter. 1. Key compromise. The private key was leaked, stolen, or otherwise exposed. 2. Personnel change. Someone with access to the key left the team or organization. 3. Misissuance. The certificate was issued to the wrong identity, or the CA detects fraud. In all 3 cases, the right action is immediate revocation and reissuance with a fresh key pair. Never reuse a key that was compromised. Certificate pinning is a hardening technique that ties a client to a specific certificate or public key. 2 flavors to know. The web pinning standard, HPKP, HTTP public key pinning, was a browser feature that let servers tell the browser, for this domain, only accept certs matching these public keys for the next N months. HPKP was retired in 2017 because operators kept bricking their own sites by pinning keys they later rotated. So HPKP is the wrong answer on the exam. It's been deprecated. But pinning in mobile apps is alive and well. iOS and Android apps embed expected public keys in code. If the cert presented at runtime does not match, the app refuses to connect. This defends against compromised CAs. Even if an attacker can issue a fake cert from a real CA, the pinned app won't trust it. You now know every concept Security Plus tests on cryptography and PKI. There is 1 chapter left. a fast review of the top exam traps and the highest value answers to memorize before walking in. Chapter 13. The 10 answers most likely to appear on Security Plus. AES 256 GCM for symmetric encryption. Always. SHA-256 for hashing. SHA-1 and MD5 are deprecated. RSA 2048 minimum, 37.2 recommended for new deployments. ECC gives the same security as RSA at a much smaller key size. Modern systems use it by default. Asymmetric encryption is for key exchange and signatures. Symmetric handles bulk data. Digital signatures means hash plus sign with your private key. Anyone with your public key can verify. The trust chain walks leaf to intermediate to a root in the browser's trust store. Self-signed certificates are only for development. For revocation, CRL is offline and stale. OCSP is real-time but leaks privacy. OCSP stapling is the modern default. And finally, TLS 1.3. Weak ciphers like RC4, CBC mode, and RSA key exchange are always wrong answers. 5 traps the exam loves. Self-signed certs for production. Wrong. Always pick DV at minimum. ECB mode for any real data. Wrong. Pick GCM. Reusing a key after compromise. Wrong. Always generate a fresh key pair. Wildcards matching multiple subdomain levels. Wrong. star.example.com matches only one level. And HPKP for new sites. Wrong. It was retired. The modern approach combines HSTS, automated renewal, and certificate monitoring instead. You came in to fix the cryptography section of Security Plus. You leave knowing AES modes, the difference between symmetric and asymmetric, hashing, digital signatures, X.509, PKI hierarchy, how to build a full CA from scratch, certificate types, TLS handshakes, and the entire revocation story. That is more depth than 95% of working IT engineers carry. Walk into the exam knowing this is your strongest section, not your weakest. If you want to keep going, practice questions, flashcards, full study guides, the link is in the description. If this video helped, hit subscribe. Good luck on the exam.